Hello, everybody. My name is Anna Federica Urbano. I am an associate professor here in Toulouse at CWRU. And I have the pleasure today to introduce Chirag Kharangate, who will give his talk. So Chirag is leading the two-phase flow and thermal management laboratory in Mechanical and Aerospace Engineering at Case Western Reserve University. He received his Ph.D. in mechanical engineering from Purdue University in 2016 and has multiple years of research and industry experience, working on projects dealing with thermal management technologies, utilizing single-phase and two-phase flows for automotive, computer, and aerospace applications. As a postdoctoral scholar in the now Nanette laboratory at Central University, he worked on the design and optimization of two-phase embedded macro-channel cooling. At CWRU, Dr. Kharangate is the recipient of the Case School of Engineering Research Award and the Office of Naval Research Young Investigator Program. He has extensive experience in testing and modeling flow boiling, flow condensation, and evaporation phase change schemes. His research interests also include understanding the effect of gravity from microgravity to hypergravity on phase change technologies. He complements his experimental theoretical work with the development of computational fluid dynamics, as well as novel machine learning tools for predicting phase change phenomena. And today, he will give a talk on the advances in phase change research to meet future thermal management needs. Please, Chirag, the floor is yours.
Oh, Chirag, I think you may be muted.
Yeah, sorry about that. So I hope you're able to see my screen. So today I'm, like Anna Federica said, I'm going to give a talk on advances in phase change research that we're doing here at Case Western to meet future thermal management needs. So I'm going to give a lot of, I'm going to go through a few topics, different topics, and also different aspects of research within those topics. Relating to fundamental research, as well as, before I conclude, a section on applications. So the talk is divided into 5 sections. At least the focus would be 3 specific sections. The first one on flow boiling. So I'll talk about, how my work in the laboratory at two-phase flow and thermal management laboratory relates to studying flow boiling, its understanding and applications to NASA, as well as Office of Naval Research. I'll follow that up with talking about fundamental questions that we are trying to address in flow condensation, both of which are basically addressing our two-phase thermal management design changes that we are proposing. And I'll go into other aspects of two-phase flows, which are more applications in two-phase flows. Also, we are working in the lab here at Case Western before concluding this talk. So basically, a lot of us do have some introduction of two-phase flows, and at least the main, the overarching importance of the work we do is that the current thermal management systems across applications, which includes the computer industry, say the defense sector, the automotive or even aerospace industry, is still relying on single-phase heat rejection techniques. And we do see that two-phase systems can provide much better, thermal management performance, basically heat transfer performance. So it can be useful, and our motivation to a lot of our work is to try to have more widespread implementation of two-phase technologies to replace the single-phase counterparts. But overall, like the industry as well as even government agencies have kept away from widespread implementation because we still lack a lot of fundamental understanding of individual effects and parameters which include geometric and operating as well as fluid behavior parameters that impact the two-phase thermal transport. So our understanding does show us that basically boiling, we can get a few orders of magnitude enhancement performance with respect to single phase, which was already better than natural convection. So a better understanding of flow systems to use these two-phase thermal management technologies can help a lot of industries. So in this talk, I have three basic, main focus areas, which I just talked about in the introduction. I'm going to divide it into flow boiling fundamentals in terms of what fundamental work we're doing in flow boiling. I'm going to start with experimental work, follow that up with like theoretical modeling, where I'll focus on one parameter, critical heat flux. And then I'll go into autonomous vision, where I'll focus on, or at least talk about heat transfer coefficient. I'm going to go follow that up with the flow condensation section, where I'll again talk about experiments, follow it up with some computational fluid dynamics simulations and data science modeling. In data science modeling, it's more data consolidation and modeling, as well as connection to physics-informed stuff that we plan to do in the future. Before I conclude the talk, I'll have a short section on different applications of boiling and condensation, just to see the scope to which these fundamental research questions can address actual applications. We work on vapor chambers, we work on electronic devices, say high heat flux device fabrication and different materials. We have applications in NASA. A lot of my projects come from NASA, where we are interested in cryogenic fluid management, condenser systems, heat exchanger systems. So first section. So in my lab, we work on a lot of questions, which come from different industries, as well as the government, which include for NASA. So NASA is a main focus area in my research group. And one thing that, where we can contribute is understanding the effect of gravity. So in the flow boiling section, as well as in the flow condensation section, in the experimental part, I'll talk about how gravity affects the flow boiling behavior. Something we all understand, but what we see terrestrially can be significantly different in microgravity. What we see in even terrestrially between different orientations can have a significant impact on both heat transfer and critical heat flux. I'll also try to talk about how we can use interfacial, instability behavior to predict performance parameters. And as I said, I'll focus on critical heat flux for that section. And then I'll also go into some work we're doing with autonomous vision in collaboration with UC Irvine, trying to find out how we can better predict, say, heat transfer coefficient. So with our experiments, I'm going to focus on, influence of Earth's gravity and on critical heat flux. I won't go into heat transfer results here, but we do have them. And I can always share those with you in some other, if you were to email me. So we have this flow conditioning loop in our lab. This is supported by, right now, has been used on NASA as well as Office of Naval Research project. It's a simple two-phase flow conditioning loop. It uses NPFH or FC72 as the working fluid. It has the common components like the gear pump, flow meter, preheater to provide the required inlet subcooling for the flow boiling module in this situation. Within the flow boiling module, we have two-phase flow, basically being generated, and then there's a condenser. It's able to support not only our boiling experiments, as I'll show, it also supports our condensation experiments. So our flow boiling module, this one specifically is designed for capturing flow visualization data in addition to data acquisition for heat transfer and pressure drop. So this is showing you like the figure on the top here. It's showing you a sandwiched configuration with two aluminum support plates compressing three legs in a transparent plastic between them. The end result is this cross section, which gives us like a flow channel which is 2.5 millimeters wide by 5 millimeters in height. We have enough length for flow development, and then in the heated section, we have capability to heat the top and bottom walls individually or simultaneously to basically provide the heating and initiate boiling. And the side walls, as I said, are transparent, allowing us to visualize this flow. We have temperature measurements as well as resistors put in such a way that we can provide almost uniform heat flux along this heater channel. So I like to go into some of these simple configuration data, like when I do it, show my experimental work, just showing you if I were to compare like a horizontal flow configuration situation where we have three different types of heating for the same setup that I just showed you. So if we have a top only wall heating configuration, this is all in Earth's gravity, you would have vapor accumulating at the wall. If you have a bottom wall heating configuration, with the flow and the waviness that it generates, we'll have vapor leaving the bottom wall and allowing liquid to basically come back and wet the wall. And in a double-sided, if we were to simultaneously heat up both the walls, you would have more of a combined behavior. And this is expected at least for lower flow rates where inertia is not dominant and gravity is. So in our flow visualization studies, we perform different experiments. This is a low velocity flow case for all these three heating configurations, shown with flow going from the left to the right and three levels of heat fluxes until we see critical heat flux. So in a simple top wall heating situation, we can see vapor generating at the wall, following a wavy vapor behavior, and liquid vapor taking a lot of the wall space as well as some liquid access along the wall. The same thing if we were to look on the bottom wall heating, it's not, we cannot easily visualize it. It's basically the vapor and liquid are mixing as well as, but we can see or expect that as the vapor goes up, the liquid is going to re-wet the wall. And that's something happening behind what we can visualize in a two-dimensional situation. And if we were to do a combined one, you can see, vapor being generated at both the walls and mixing, and, the behavior being more of, at least not clearly visible here because of the dominance of the vapor generated at the bottom wall. But we can look at how the boiling is happening. One clear thing to notice is the clear difference in critical heat flux. It's 10 watts per centimeter square in this configuration, as we expect liquid has less access to the wall and it loses access before these other configurations. The best behavior is still the bottom wall heating. As expected, even in a pool boiling situation, the vapor can easily leave the wall. And here we have a flow aiding the vapor removal. We have more of a moderate critical heat flux in this central configuration. We expect, and basically, even if one of the wall triggers CHF, we turn off the system. So this 18 watts is basically observed at the top wall. And that's when we turn off the system. So now if we just move to a higher velocity, these velocities are important to us in some of the work that we do with NASA, because if we were to get configurations where velocities, where inertia starts to dominate gravity, a system that works at -1g, like top wall heating, would also work well in 0g, at least as a starting point. That's how we design some of our experiments for these space systems. In this situation, we have 4 times the velocity, almost 1 meter per second square, meter per second compared to the last one. And now the behavior is, as you can see, is closer. Inertia is starting to become dominant. It's not exactly the same yet, but much closer than what we saw in the last configuration. And in the double-sided heating wall configuration, it's more like, larger shear, larger mixing. But overall, even the critical heat flux values are starting to converge. So these are some things that we use to study the behavior, look at how the interfaces and the phases are behaving as we perform these different heat transfer experiments. So we, as we come close to the end of this section, I just want to say we perform these experiments for different inlet conditions, which can include high subcooling, low subcooling, and even two-phase inlet. In all of them, at some point, we can see critical heat flux values for all these configurations starting to converge. More or less, the point at which inertia starts to dominate is significantly impacted by what the inlet condition was. But we are able to design systems or talk about systems where gravity no longer affects this important design parameter. more or less these threshold velocities help us to design thermal systems for 0G as a first starting point. So now I'll move, I have multiple sections, all of them related, but go into different aspects of it. Now, I'm going to talk about, say, modeling critical heat flux, or basically a hydrodynamic instability model to predict critical heat flux. And we'll use the same behavior that we saw in our last slide. This is what we observe for a single-sided heating, and the one on the left, and on the right, we observe the behavior for a double-sided heating. You have liquid coming in, vapor being generated, and having a wavy vapor behavior, at least except for not easily being able to visualize the bottom flow. For most cases, this was the behavior we saw. There was vapor contact region, where we would expect mostly vapor being in touch with the wall, with intermediate sections where liquid would be wetting. So this is where most of our liquid access is coming in to prevent anything, a phenomena like critical heat flux, basically due to departure from nucleate boiling, from happening. So looking at that behavior from the images, we set up a combination of separated flow and interfacial instability. But like I said, what we do see in our imaging, and when we see CHF, when we turn systems off, there is very little liquid access that we see at the wall. So if this were to be a simple, a wall, before critical heat flux, there is wetting at the wall, and it can include vapor bubbles, but still liquid clearly being seen at the wall. After critical heat flux, we are saying that the vapor no longer hits the wall. So this specific model that I'm going to talk about states that the CHF is triggered when liquid no longer has access to the wall, and liquid can have access in two directions. So one direction is basically in the flow direction. So as new liquid comes in, it can, it will have access to reach the wall. And as if that access is cut, the vapor would, that liquid won't reach it. And then in the perpendicular to the flow direction, again, as vapor bubbles are generated, the liquid re-wets the wall. As vapor comes out, it comes back to the wall, and that is another access point. So CHF, according to the model, is triggered when both these axes are cut. So the first part of it, we do instability analysis. Let's just consider like a simple configuration, liquid moving along the wall. We do an instability analysis with mass, momentum, and energy with slip flow, formulation, assumptions. So more or less, we are interested only in the mean velocities and mean vapor thickness in this situation. We do the analysis to find out what would be the variation of different layers, as well as the liquid layer, the vapor layer, the velocity, and the pressure drop along the channel. In the first part of the instability study, we talk about in the flow direction. So in the flow direction, we have these vapor being generated, having a wavy vapor behavior. As long as this interface that we're talking about, like you're seeing, is unstable, it's going to touch the wall, because unstable would mean that it will always try to, have access to the wall. When it becomes stable, which would mean it would try to flatten out, it's when in this flow direction, the CHF would occur. So the transition from instability to stability gives us this, from a classic interfacial instability theory, the wavelength at which that will happen. And that is the first number that we get out from this part of the model. Now, we combine that with what is happening in the wetting front in the other direction. So as we saw those images, within the wetting front, it's mostly liquid that's on top of these vapor bubbles which are generated at the wall. So within that, if we consider a moving frame of reference with the vapor not having significant shear force on the liquid domain, we can model it similar to our our Zuber instability study, where we talk about the CHF being triggered when these bubbles which are generated at the wall, they merge and generate a vapor blanket. So we use within that frame of reference, which is the wetting front in the perpendicular direction, Zuber pool boiling model to get the value for critical heat flux. So combining both these wavelengths within this section, we are able to predict CHF, which we compared for different experiments that we performed. This included experiments in horizontal flow, the ones that I just showed you, with double-sided heating, bottom heating, top heating, for vertical upflow conditions, as well as in microgravity conditions. Overall, any of these models, their prediction capability, like the prediction numbers are within like 15%, which is significantly better than any traditional, just a correlation-based technique in such configurations. So with that, I'm going to now move to another section. So this talked about, modeling CHF theoretically. Now let's talk about something, new that we've been doing for the last couple of years. I'll go into, utilizing data from, say machine learning. Here, the flow boiling part talks about autonomous vision. So we are able to capture more information from autonomous vision tools compared to our, traditional techniques, and how we can use them is what this section will talk about. But we do know that, like just comparing different boiling behaviors, you could have a behavior that's nucleate boiling versus convective boiling, just if you were to change, say, the dimensions of the channel or the fluid type. And these things significantly impact, designing like just universal tools for our performance parameters. So here, investigating and studying the specific flow behavior may and can help us, we think, in improving our design tools. So this is a collaborative effort with UC Irvine and Yunjin Won. Basically, we use our flow, we give our flow visualization image data to extract information from these images. So this is just showing you the boiling behavior that we saw. You can see, there is multiple of these vapor voids and liquid on in the channel. That we develop an object detection module and a tracking module that tracks the bubbles or the vapor within this section. With that, we are able to, then look at different information. Like here, we are showing the void fraction variation. This is the mean variation for a specific flow rate, and statistical variation is also captured. We can capture the length of these vapor sections. We can capture the area around this vapor. If we were to study the interfacial, waviness, the wetting fronts, and you can use that for different parameters. We use that for parameters like critical heat flux as well. But today I'll talk about, say, heat transfer. So if I were to just look at our heat transfer predictions from these models, like this is showing you, if I were to just look at a traditional correlation technique to just predict the heat transfer, these square dots are the heat transfer from one of these experiments at a like moderate heat flux, I would say not at CHF, like 70%. And if we use any traditional like correlation, first of all, it's not able to capture the trend. And second, even the data can be off. So one main thing that we are seeing is all of our correlations are specific and may be developed for certain channel or boiling configurations, which may not apply outside their range. We do understand that. But why is it that none of them, or they are not able to capture? And here we can use some of the information to understand why can these trends be captured from these images. So if we look at this image, we can see one thing for sure. You have more wetting in the inlet region, and this wetting reduces as we go in the exit region. So the amount of wetting changes. So we can basically use this behavior to try to find a net heat transfer that's based on how much time the vapor is at the wall and how much time there is wetting. So instead of using just a straightforward correlation, we could find out the ratio of time for two-phase behavior and the ratio of time multiplier for single-phase behavior. And when we use that, all the correlations basically start capturing this, high heat transfer at the inlet region and low at the back. There's further improvement needed, but we are now at least seeing, this specific behavior that happens in these configurations, in flow configurations, and if we were to understand and use them in our modeling techniques, we can get better information. And mostly what we used here is basically, this information of like wetting. So there was more wetting and less vapor. And we also try to use the velocities of both of these phases. Here we're using the model results. If we have, say, particle image velocimetry data for one of the phases, we could use that. But with that data itself, we are able to at least now improve our prediction of, say, the trends that we get from these tools. Okay, so this concludes the section on flow boiling. I talked about, why gravity is important to the work that we do with NASA, and I showed you how, at which velocities or how, higher velocities inertia becomes dominant. I talked about the instability analysis that we use to predict critical heat flux in this case, how the model used a combination of, instabilities in vertical and the horizontal direction to the flow to predict CHF. Went quickly into vision data where we, instead of using any manual techniques to understand the images, we used autonomous vision to extract information from the images and then use it to improve or understand our predicting capabilities for heat transfer. There's a lot of other work that we do, but and there are next steps in some of the work that I showed, which includes, more diagnostic techniques and using that result in modeling and CFD modeling, which I'm not going into today, but it's part of the work that we do relating to fundamentals in flow boiling. I'm going to move to the second section, and these sections I'm going to go more quicker than boiling. I do try to stay longer on the boiling section. In condensation, again, I'm going to talk about how gravity affects the behavior. We do understand how important it is, but for us in the lab, it relates a lot to NASA and the needs of NASA. So another thing that we want to improve in condensation is the same thing like performance parameters. So our understanding of two-phase behavior and interfacial behavior on turbulence around the interface can significantly change what is the heat transfer. And that's something we want to study, experimentally get data, as well as capture it using computational tools if possible. And I'll conclude this section with a small data science, basically data modeling aspect, which we apply to condensation. So with experiments, our importance and focus is capturing the interfacial behavior. And condensers play a significantly important role in heat rejection systems across applications. Anyway, you're going to have a boiling system, you need a condenser for the heat rejection. So this is the same experimental facility. The one that I showed you, the only thing changed is updated here is the condensation module. So we have the same system. It's able to provide enough heat to completely convert this to vapor or give two-phase inlet to our test section. We have a tube-in-tube condenser configuration with inner tube having the working fluid, FC72. It's a cross-flow heat exchanger, and the outer tube having water. Wall temperature measurements, as well as the water temperature measurements, allow us the capability to estimate the heat flux and the corresponding heat transfer coefficient. So we do, we've performed a lot of experiments, on different projects with respect to what happens to the interface. The behavior in condensation, to study it, is more complex and is highly more turbulent, I would say, compared to what we see in boiling. But basically, we do capture strong interfacial waves moving along the channel, and our channel configuration also impacts how well we can visualize it. Like a curved surface, etc., has more, curvature effects that we are not able to remove when we get them to images. But we study terrestrial horizontal data where we can see how gravity would affect differently on the top side versus the bottom side. Microgravity data, this is not very high quality, but we have more axisymmetric behavior, but we study them for different flow rates, different conditions to capture the interfacial behavior. One important part of what we want to study, like at least in my lab, we are trying to understand is how much, and this is part of not only this experimental study, but also the computational study, is how much the interface affects, say, the turbulent behavior. So if this is a condensing wall, you have liquid followed by vapor. This is the liquid film in this film condensation scenario. If the interface has no impact on the turbulence, then we would expect basically the eddy diffusivity to have this no slope at the interface. We know that the eddy diffusivity dampens at the wall. So one theory, or there are some theories which state that the eddy diffusivity also can dampen at the interface. So different levels of dampening can lead to different behaviors around this interface. And for no dampening, you can get a temperature which is much higher than very high dampening. And so how much this moving interface impacts the turbulence behavior can significantly change what is the final temperature or the heat transfer coefficient in condensation. Experimentally, we measure it, and computationally, we try to estimate it. I'm not going to go into the results in this section, but this is one important aspect of condensation that we are trying to investigate in the lab. With respect to CFD, here I'm going to show you initial data that we got with 2D CFD modeling of the same configuration. We used the data from a vertical upflow configuration. This is a 2D axisymmetric domain. Used a simple, the basic Lie models to estimate the mass transfer. Applied our, traditional turbulence modeling, as well as the conditions, inlet and boundary conditions based on experiments. And we are able to predict experimental behavior and computational behavior. Overall, as you can see, we are not able to very well predict the local behavior. And all of this is also impacted by the film temperature variation. Like I showed you that, this plot here, if we are using different levels of dampening, we get different behavior from our CFD models themselves. So we try to tune them in some of our future studies. It is dampened here, but this rate of dampening we are able to modify and study. If we dampen it more on one side versus the other, we are able to better tune these results. But it's not a consistent thing or one number for all configurations. So our understanding of this needs to improve, something we plan to get out from experiments. But the models itself also capture this, interfacial dampening. The film thicknesses are different at different locations. That's why they are not very clean to visualize. But still, we look at what we capture using computation, compare it to our experiments with respect to our parameters of interest here, which would be heat transfer and pressure drop. The fluent itself also can capture our, at least the complex interfacial behavior. There is no, I would say, quantitative comparison that we can get with these images, but at least something to start off to see if our behavior, which we see in experiments, is observed in the CFD. The local average predictions of heat transfer are reasonable, but as you saw, the mean or the average behavior is reasonable, but the local is not. And that's where significant improvements are needed in our CFD, as well as our understanding of these models to predict or improve our predicting capability. I'm going to talk about now another section. Now this again relates to data science, but here I'm going to go into what we do with data consolidation. So in the first section, we used autonomous vision to extract new information using vision tools. Here for condensation, we've done this for boiling as well, but for condensation, we went another way and we said, let's look at all the data that's available. And instead of generating a correlation, we can develop, say, a machine learning model. We were able to, get all published data that was available when this paper was published, like 37 published sources for flow condensation, picked up heat transfer coefficient data, which was around close to 4,900 points. And it included all of these working fluids, almost like, I think, up to 15 working fluids, large range of reduced pressures and different conditions. We investigated them, using, the correlation maps. We also looked at features and studied how, looked at how the data is spread. Like, this is just showing you like R134A being a very dominant fluid in most of our studies, horizontal being a very common configuration with most studies in there. And just we look at them so that when we make judgment on the model behavior, we can go back and, link some of the reasons for why they do well or do not. simple things using, simple training data, the models themselves can predict better than correlations. And even if we were to modify the traditional correlations, like Kim and Mudawar, they cannot really match the 10% errors that we can get with most of the, advanced models, which would include neural networks or gradient boosting models. One thing though that we wanted to see is, do they generalize? And that's where the main thing is seen. If we were to remove data from fluids like R134A, the models, still are able to, like, this is capturing the local trend. So the complete database is removed from training, and the model is able to capture that, these both neural networks, the trend as well as the data itself in most cases. This is because this fluid is significantly, has enough data in the training, location that, like training database, that it's not going to make a significant mistake. However, if we were to do this for a fluid where there's less data, maybe 1 or 2 databases or 3 databases, our correlations are still doing better, because if you do not give this fluid, which doesn't have enough parametric variations, they don't do well. And this is where we are implementing some things like theoretical model predictions. I'm not going to go into detail today, but we implement theoretical model predictions. I'll quickly talk about it in one slide, which take these things much closer to this. But at least the initial results from these data models showed us these trends, and we were able to, at least improve our design tools in such situations. So overall, like through this section, I talked about gravity playing an important role. We also talked about how we can improve our understanding of phase change if we were to better understand the interfacial behavior in these complex, basically very high flow rate, flow situations. I talked about machine learning data tools to get better predictions, but its limitations as well. And in the future, this work will lead to more physics-based implementation, and more than what I will show today. Basically, we have a lot of physics implementation and machine learning in the future. And also, better CFD modeling, not just limiting them to what we're doing, like what I showed you in 2D here. So the next section, which I'm going to go over quickly, is now, these are many of the fundamental questions that we are trying to address in boiling, for flow boiling as well as flow condensation. But there are many things that we apply it to, all of which boiling and condensation basically play a significant role. So one of them is a work where we do with, which we are currently doing with Advanced Cooling Technologies, and is a NASA project where we are trying to design heat pipes for space applications. So this one is a vapor conductance heat pipe system, which has basically a non-condensable gas. And these are very useful in space because they, the pressure in the system or the heating level can change the pressure and the amount of, NCG region, contact region, which would basically make them very like actively respond to the heating power. So during cold nights on the moon, you don't want the system to like operate. You can turn off the system, but you need low powers to keep all our electronics at a safe temperature. However, when we tried to do microgravity tests with this, basically this failed, because if you were to turn the system off, diffusion would have all of this vapor, liquid, the working fluid and the NCG to mix. Just thermal diffusion, not just thermal diffusion, just normal, phase diffusion. So we designed a new concept that would operate in microgravity. So it's basically like an external loop connected through this system. It generates a flow within the loop. So when you turn on the heat pipe, it would force out all the NCG in this region, like slowly, and then basically that NCG would the working fluid would condense, but the NCG would stay as we go through the system. So it was more like an active, heat pipe without any real pump. There is work that we are doing with cryogenic fluid management for NASA. NASA is planning these fuel depots in space, and the plan is to basically take spacecrafts, collect fuel, say around in a fuel depot around the moon, and then take them to Mars. Now, one big challenge or multiple challenges here are the temperatures at which these fuel depots as well as the transfer lines between the fuel depots or between the spacecraft and the fuel depots would be. So their temperatures are much higher than the saturation temperature of the fluid, which leads to a lot of boiling behavior and even condensation, in some situations. So we are designing an experiment for the International Space Station to study how microgravity would affect the transfer line process. So in this specific example, I'm just showing you, we try to understand as the liquid comes in and boils, the transfer line process would have it, start in the film boiling domain, go through transition boiling, nucleate boiling, and then single phase. This is when the chill down process basically completes. So understanding this to reduce the amount of vapor being generated is one aspect of it. Being able to predict this is also important, because as it boils, you're going to increase and pressurize the system. So you do not want it. The only way to save the system when it significantly pressurizes is venting, and venting is losing cryogens, which is what we don't want to lose cryogen just because we were transferring it. A similar and a related, like there are two projects which are more like STTR grants from NASA. We're trying to understand what's happening in the tank. One is to predict the heat transfer and say the spool boiling curve within this tank using, using data experiments and, simple correlation techniques, as well as, performing CFD of the two-phase behavior in the tank to improve our interfacial, just like we study for condensation, how the interface impacts just, these spray as well as different aspects of tank fill and tank, transfer process. Some other aspects of the work include, just device development. This includes like for heat exchangers using materials like silicon nitride. So we're doing tape lamination techniques to develop these manifold microchannels at small scales, and like other additive manufacturing techniques to make heat exchanger systems as well as say embedded electronic systems with silicon nitride. This is through Office of Naval Research. There's a NASA project where we are trying to make similar channels through traditional microfabrication techniques on silicon carbide. So this is just like the initial example of silicon, but we are able to make silicon carbide channels and manifold channels within them. But more or less the aim for NASA here is like electronic aircraft, like basically all electric aircrafts, and their need for like silicon carbide being a very useful wide bandgap material for their future electronics, power electronics. Just before, like one thing I wanted to add to that condensation section is a simple way where we are incorporating, the machine learning. A simplistic way is to even use, say, a theoretical model prediction to train our machine learning. And this is part of this Office of Naval Research project where we try to see if just doing that, we are able to improve predictions. And we were able to see that just traditional tools can be improved. But that specific project also addresses the fundamental aspect of the interfacial temperature behavior. So we are doing experiments to capture how the interface affects the turbulence and temperature behavior around it, and then develop new models as well. But just to give you an example, machine learning can also improve with those, with just theoretical tools, but we need to see how applicable they are to a specific situation. In a large sense, my group does want to understand boiling and condensation for NASA and apply it to their future, nuclear, thermal propulsion and electrical propulsion technologies. In all those technologies, boiling, condensation will and is going to play a critical role. So just fundamental understanding of all of these parameters through experiments, modeling, CFD, data science is the main goal of our research group. So I talked about through all these sections, I talked about, all aspects of research in boiling, condensation, and touched upon each of them, to some detail. I know that I didn't go into very specific detail on some of them, but I wanted to just give you a good overview. But I did touch upon everything, and basically I do want to, I think we're on good time. So I do want to acknowledge my students as well as collaborators on these various projects and the funding that we have received from NSF, ONR, NASA, as well as through companies, advanced cooling technologies and Creare. I think that concludes my talk, and I think I've done good with time, so I can take enough questions.
Thanks a lot, Chirag, for this nice talk. We can now open the discussion. I think we have yet a question actually from Professor Marengo. Do you want me to read it, Marco, or maybe you want to ask yourself? I don't know how you proceed usually.
Yeah, thank you, Anna Federica.
You're welcome.
Yeah, there are many questions about the CFD. You touched the CFD side of your work, but I would like to know a little bit more about that. So, did you use OpenFOAM? Which kind of software did you use? This is the first question, maybe, and then the second question is about in case of condensation. I know that usually the simulations are quite long with respect to the boiling simulation. So something more about the computational times and also the effect of the thermal resistance. So how did you treat the thermal resistance with the condensation? And finally, the other question is about the nuclei on the surface for condensation and boiling. How did you treat the seeds and so on? So there are many questions. So in fact, there is maybe one single question, a little bit more details about the CFD.
Okay. Yeah. Thank you, Marco. Basically, first question. So about the okay. So in condensation, at least what I showed you today was a 2D axisymmetric domain. We ran these simulations in ANSYS Fluent, and the user-defined functions were set up to do the mass transfer modeling. The CFD domain for this like almost a meter length tube in earlier would run like even on a supercomputer where we use around 40 cores would run for 15 to 20 days to reach a reasonable, I would say, steady state behavior. It would have a mesh size which would be in 1 million or 1.5 million just to get enough fine cells at the wall and around the interface. The results do just from what you see, the results do show us that there are limitations in 2D, which I didn't go into too much detail, but there is some limitations like the 2D behavior does not really match what we would see in 3D. So there is a significant need for doing 3D, but just with the computational effort, we might need months to reach one simulation result, and we might need to run a much shorter test section. But that's something that's ongoing currently. We are trying to run like a small inlet part of the test section to investigate it and study it. With respect to the nucleation, in this situation, the model itself, it's not trying, because that's why I still have not done a lot of boiling simulations, because there it does become far more important. We are not trying to have, I would say, dropwise condensation behavior, but a film behavior. So we let the model just use the saturation temperature to initiate condensation here. And it is not, I would say, perfect, but for now, for this film flow situation, it's okay to, at least initiate the film boiling, film condensation at a certain specific length where the temperature goes below saturation.
Thank you.
Thanks. Do we have other questions? Maybe you can raise your hand or write in the chat if you want to ask a question. Maybe I can ask one while the audience maybe have other questions. So thanks a lot for your presentation. I was curious about the experiments that you are planning to carry out with respect to depot application, so in the ISS. So if I understood correctly, actually the experiment in the ISS is meant to study the transfer only, and you have other experiments on the thermal management of the tank itself in other environment, which I guess is in microgravity. So I was curious to know a little bit more also about that experiment. So if you're planning to study, yes, Boeing and cavitation, test tanks, or what, and with which fluids you are planning to use, if only a refrigerant, or if you're planning to do some cryogenic fluids experiments. Well, I guess not in the ISS, but maybe in other platforms. Yeah.
Okay, so yeah, with respect to the specific ISS, we cannot do any cryogenic testing there.
Yeah.
But recently they have they basically have the flow boiling and condensation experimental facility that has been set up on the space station. It's able to provide, similar to what I showed you with a boiling or condensation test. It's able to provide two-phase inlet or vapor or liquid inlet or completely vapor inlet to a channel. So we are designing a facility that will go and replace the flow boiling module to be able to study chill down. The working fluid is a refrigerant. So what we are doing is we are taking the same refrigerant like FC72 and we are heating up our test section. There are quite a lot of details, but I'll just go into the simple ones. Basically, we heat up our test section to be in the film boiling domain. So if the refrigerant is at 56 degrees centigrade, we heat it up to 250 degrees centigrade and then flow the fluid through it. As we go through look at the temperature, we go through this chill down curve, which includes the film boiling, transition boiling, CHF, nucleate boiling, and single phase before chilling down. So our idea is to be able to capture this curve, understand different aspects, including flow visualization data. There are two test sections, a flow visualization test section and a heat transfer test section. So we can study each of these domains individually, model them, as well as we have CFD tools to complement it. With respect to the tank work, they're also using for ISS the same things, but with the parabolic flights, we are doing tests with like tanks or even transfer lines with nitrogen. So it's also, nitrogen is the fluid that will be allowed, but we are not studying cavitation, etc. But like at least my lab focus and the work we do is to be able to predict the heat transfer behavior. So just the can we predict all of these aspects of the curve, which would be different, say, in a heating situation versus a quenching, and concentrate on the boiling, condensation parts of it.
Okay, thank you. I see that we have another question from Zengamaulu. Please, you can ask your question.
Thank you. Yeah, very nice talk, Chirag. So for the cryogenic part, I guess I'm curious, would you expect any different physics in terms of, for example, the shape of the curve for the boiling, or do you think is mostly the challenges for the materials that have to work at that temperature? This is my first question. Yeah.
So the behavior, so when we do a simple boiling, say an experiment, say a heat flux control surface or a temperature control surface, you test out, go to different heat fluxes or temperatures and go along this curve. In a quenching situation, we just let the system with its thermal mass quench through the process. The thickness of the channel, the material, the surface, all of them significantly change each of these points, the CHF, Leidenfrost point, the individual domains. So the behavior is just data analysis showed that the CHF is, for a thick channel, is 70% of a boiling behavior, say a heating. So 70% is for a thick channel, and real cryogenic tanks and transfer lines are very thin, where the thickness is going to also affect each of these parameters. So whatever we are going to get or what we are getting in the lab also does not match the traditional correlation results for any of these domains. So it cannot predict it. So either we just have, NASA will have to just do experiments and use that data for each individual test case, or what we are doing here is to be able to develop some physics that can predict this behavior. That's the reason it needs to be done separately.
Okay, thank you. My second question is about the simulation. So I'm wondering, what type of boundary condition you put at the interface and between the liquid and vapor, and how sensitive your results is to that.
So with simulations, there is no boundary condition at the interface, but what we are trying to see is that the interface is saturated. So to get it to saturation, in case of a simple model like the one we use, Lee model, we would increase the Lee coefficient. So that's just one, so here in this kind of a simple situation, we would increase the Lee model to allow saturation. So in equilibrium, we expect that, in a fully developed case, the temperature would try to be saturated. And that's why in this situation, as long as we reach saturation, that was what we allowed our simulations to, use that to set up the boundary condition. Yeah, it's not really set up, but we tune it manually. Now we are using, some other tools like machine learning to predict RI, and change along the channel. Something, it's very new and we're trying it. I don't have results for it now.
Okay, thank you.
Okay, maybe we have time for a last question from Adia Kartikeyan. Sorry for my wrong spelling of your name.
Thank you, Chirag, for the great talk. My question is on the boiling part where you were using machine learning to predict the heat transfer. So in that case, when you were seeing that the area wetted and the area covered by liquid and that covered by vapor, I am curious how the microlayer wetting was taken into account. So when you say there's a vapor area, yeah.
So yeah, in this specific, like what we have shown here, I haven't gone into, because we are still using traditional correlations. Some of them may be using microlayer, some of them maybe not. But through the what we saw, we are able to at least find out where there is no liquid, or at least no liquid wetting, versus the other section where if I were to go close, there is boiling happening at each of these individual sections. These images are not showing it. So we just use the correlations to use these average variation behavior of the wetting fronts and the waves, the vapor waves, to predict heat transfer using the traditional techniques. Like you said, at this point, we are not really capturing everything exactly. There's some more higher error also in the inlet and outlet data that we get from machine learning. But this now can be taken to that step where you are saying, where we could use specific microlayer models and target them to see which microlayer model is giving better boiling behavior within this region. Now, with the traditional ones, we could not do that at all, because anyway, the trends were also not captured and the behavior also did not. So with this, our next step would be, yes, now target specific, I would say, mechanistic models for heat transfer and improve it. But at least we went this one step just by this vision data. And I think that was like a very good, like it's a good move. I was very happy that I think this can be taken further.
No, absolutely. I was curious if this can be done on a dynamic scale, like continuously do this, capture this data of like where the vapor is forming and where the liquid is wetting. So this is going to give
exactly. And here we are also, basically this is showing you averaged behavior, but we have all the statistical information. And then we use the time averaging, how much time it's wetted versus dry to find the correlation. So just if I were to just use a distance, it doesn't work. So just so you know, like how much time it has vapor versus liquid really is more accurate, and it did work out better.
This is very cool. It's very interesting to watch that. Thank you.
There is a last question I think that we can take from Stefano Paulice about machine learning. Maybe Stefano, you can ask your question.
Yes. Can you hear me?
Yes.
Yes.
Okay. No, what about machine learning? Why? My question is, what we are missing to have a full machine learning tools to have a good prediction, or to achieve and get new correlation, efficient and reliable new correlation with a full tool with machine learning and your tool of vision machine learning. So what's missing for you, in your opinion?
So like this now, like just take every part of machine learning has parts missing. So in this part, I'm taking 2D images and visualizing from the side. So I am going to miss out, like in this in the boiling scenario, I'm still clearly able to see that the vapor is covering the whole channel, so I can get most of the information. But if instead of this, I were to just visualize, say, the wall, the bottom wall, and it was transparent, I will be able to get better information on the wetting versus dry regions. So better diagnostic to capture the wetting versus dry regions, better 2D to 3D convergence of these images. We need to use different tools to do 2D to 3D translation of these images, will further improve the quality. So we are still limited to, in even what I'm showing is to 2D image. So it's not like it might be accurate within 5-10%, and that itself is some error, even though better than what we had in the past. This is one part. With the data science, there's just like data itself is not enough.
Maybe more images in the tangential direction.
Yeah,
Because
and images is one part of it. If we can get velocities, if we can get the thermometry, those things can further validate our results. So there's a lot of experimental inputs that can lead to this, and that can improve it further. Like even this is showing some movement for us, which is encouraging, and we think there are many avenues which traditional techniques could not by themselves capture.
Well, thank you, Professor.
Thanks, everybody. So that was the last question. So thanks for attending.